Hello, everybody, and welcome back to Holistic Healing by Tiamat. We are here back again with how to build a healthy brain. So, this is the third episode of how to build a healthy brain, and we are now getting into chapter number 3. Okay, so chapter number 3, getting to know the brain. Imagine you are walking down the street listening to music. Your brain is interpreting the information coming in from your eyes about the conditions of the pavement. Is it gravel or is it paved? Is there a lamp post coming up that you need to avoid? Is it then coordinating this information with the sensory data coming in from your feet and legs, making your judgments about how much pressure to apply to the ground and how and when to bend or extend your knees? Specialized areas of your brain will be holding in mind your destination and what you expect to happen when you get there. At the same time, the tiny vibrations created by the sound waves as they hit your eardrums are translated into electrical signals that will be further interpreted into music or words. Receptors in your skin relay information about the air temperature, and your brain makes a decision about whether you should button up your coat or take off your scarf to help regulate your internal body temperature. At the same time, a vast network of messages are being exchanged about other important internal conditions. The relative availability of water or glucose in the blood will translate to a conscious awareness of thirst or hunger. The accumulation of certain molecules in the brain translates into varying degrees of alertness or a desire to sleep. Interoception, the perception of what is happening inside the body, will indicate hunger, satiety, or the need to pee. This activity doesn't stop when you close your eyes and go to sleep. Far from it. As your brain moves through the different levels of sleep, which we will get into on page 69 for more information, it begins the nightly processes of reorganizing the events of the day. Important details and information are included. We will go to page number 69 to talk about the different stages of sleep. So, you've got the light stages of sleep, which are stages 1 and 2, and then you've got the deep stages of sleep, which are stages 3 and 4. I will go into more detail about these later on within these. However, when you are awake, your brain has a lot of activity going on in it, as I will show you within this photo here. This is your brain when you are awake. Now, these are your brain in stages 1 and stages 2 of sleep, so the light stages of sleep. And these are your brain in stages 3 and REM, so in the deeper stages of sleep. Very relaxed brain, which some of you may already be in already. Not obviously in the REM stages, but in the more deeper stages of sleep. Although this is only 4 minutes long so far, so you're probably not that deep into sleep yet. But Interoception, the perception of what is happening inside the body, will indicate hunger, satiety, or the need, satiety, or the need to pee. This activity doesn't stop when you close your eyes and go to sleep. Far from it, as your brain moves through the different levels of sleep that we just mentioned, it begins the nightly process of reorganizing the events of the day. Important details and information are encoded, while insignificant ones are archived or allowed to fade. Furthermore, during sleep, your brain undergoes a deep clean, clearing away the accumulated debris of the day, helping to keep your brain healthy. The human brain is the most complex structure in the known universe. This is why it is always astounding to me when people expect themselves to be completely in control and to understand their own minds. Most people don't understand their phones, so why would you expect yourself to understand an organ that is many hundred times more complex? Nonetheless, it will be helpful for you to know a little bit of neuroanatomy to help you get the most out of this book. That way, as you move through the chapters, you will have a better sense of the physical actions that all of the tips and habits are exerting on your brain, and you will better understand why it is so important. This is a motor neuron. This is a dendrite, the little hairs at the top of a motor neuron. The nucleus is located inside of the motor neuron. You've got the cellular body, which is just outside of the nucleus. And then you've got the myelin sheath here, and the Schwann cell, the node of Ranavar, the axon, and then you've got the axon terminal at the end there, the synapse. So that's obviously how we make connections within our brain through the motor neurons. I didn't know that. This is the receptor neuron, postsynaptic it's called, and this is called a messenger neuron, postsynaptic. At the synapse, here at the synapse, the direction of action is going downwards, potentialing the signal. This here is called the vesicle, the little dots, and this is called the axon terminal. The neurotransmitter, which could be serotonin, is what is going in between the receptor and the terminal, and this is the receptor. And this is the dendrite, which is the receptor neuron at the bottom here. As the action potential travels along the axon, it triggers vesicles, which are sacs containing the neurotransmitter, to fuse with the synaptic membrane. The neurotransmitter is released and drifts across the synaptic cleft, where some dock to receptors, triggering a new action potential. Some of the neurotransmitter drifts back to the presynaptic neuron, which is then replaced/reuptaken. There are several types of cell in the brain, each playing an important role and complementary role to the other. This type of cell that most people are familiar with is the nerve cell or neuron. Neurons are couriers in the brain system. They are responsible for relaying messages to and from the brain and the body. Neurons have a soma, or cell body, that contains the nucleus. The nucleus contains the cell's DNA, the packet of information that tells the cell what to do. The branch-like projections, dendrites, receive the information from the preceding cell in the form of chemicals called neurotransmitters that initiate an electrical impulse. This electrical impulse, action potential, travels down the axon towards the axon terminal. Within the axon terminal there are sacs called vesicles that are filled with the neurotransmitter that the cell is specialized to produce. The arrival of the action potential at the axon terminal causes the vesicle to move towards the edge/membrane of the axon terminal, where it then fuses membrane, so it fuses membrane. So as this neurotransmitter fuses with the membrane, as this compound fuses, it releases the neurotransmitter into the space between the axon terminal of the first cell and the dendrite of the next one. This space is referred to as the synaptic cleft or synapse. The neurotransmitter molecules drift across the synapse and connect with receptors on the dendrites of the postsynaptic neuron. When the neurotransmitter binds with the receptor, it triggers an action potential in the axon of the postsynaptic neuron, and the process then continues. The axon can be thought of as a wire or cable sending an electrical signal from one end to the other. Similarly, the axon is insulated like the plastic around your household wires. The insulation around an axon is a fat-based substance called myelin, which helps to increase the speed at which the action potential travels down the axon. Glia. Glia are brain cells that do not send messages but help to protect and support the function of neurons. Some types of glia are astrocytes, oligodendrocytes, and microglia. I'll just highlight a couple of their functions as they will be relevant later on. Astrocytes. One of the main functions of astrocytes is maintaining the physical shape of the brain, but they are also important for the development and survival of neurons and can increase the strength and activity of synapses, as well as their overall development. Astrocytes feed neurons by extracting nutrients from the blood and passing them to neurons. They are also available to produce glucose, the preferred form of energy for nerve cells. Oligodendrocytes. This type of glial cell produces two proteins called brain-derived neurotrophic factor (BDNF) and insulin-like growth factor 1 (IGF-1). These proteins promote the growth of new neurons and connections, synapses, and support the survival of the ones we already have. This is hugely important because, as you will come to see, protecting the brain cells we already have is the best hope we have of securing long-term brain health. In the brain and spinal cord, oligodendrocytes produce the myelin that wraps around the axon. Microglia make up about 15% of the brain and play an important role in the brain's immune response. Microglia have long branches that stretch out and monitor the conditions around nearby nerve cells. When they notice a problem, one of the things they do is engulf or eat harmful agents within the brain, such as bacteria from an infection. A process called phagocytosis. They are also able to fight off unwanted pathogens by releasing powerful toxic chemicals. However, if this process goes unchecked, these chemicals can actually harm neurons. We'll talk about the circumstances under which this happens in Chapter 5. When they are activated by the presence of bacteria, a virus, or a brain injury, these microglia multiply and release compounds called cytokines. Cytokines are the group name for a number of different proteins that play a crucial role in our immune system's response to illness or injury. When the threat is controlled, the microglial signal for the start of repair processes to fix the damage has occurred. The blood-brain barrier. The membranes around most body cells and the lining of blood vessels are partially permeable, which means they allow water and some other molecules through. This allows the water that you drink to pass through the blood vessels and to reach the dehydrated cells in your fingertips, for example. These particularly permeable membranes are like the friendly doormen at a nightclub. They'll check your ID and they'll let you through. Your brain, however, is incredibly selective about what it allows in. Instead of a friendly doorman, the tight junctions of the blood-brain barrier, BBB, are more like a fingerprint scanner at an exclusive private memberships club. Only an elite and the few can gain entry. There are handfuls of important are discussed on page 200. Okay, so we will speak about this tomorrow and we will end this today at the blood-brain barrier. So yes, this exclusivity means that even cells that form part of the body's immune system can't even get through. This is one of the reasons why the brain has developed its own immune defense system, and in the form of microglia. This selectiveness is essential because the brain is so important and vulnerable to damage that you do not want to risk important and vulnerable to damage that you do not want to risk exposing it to anything that might cause it harm. If something happens to the body that impairs the function of the BBB, there may be negative consequences. Interference with the action potential of the neurons. Depending on what part of the brain is affected, this can contribute to impairments in thinking or movement. Immune cells from the body's immune system can get through the brain, since this is not where they belong. This can create a lot of confusion. Either they can mistakenly attack healthy brain tissue, or the brain's own immune cells will attack them. And sometimes both of this happens. And if this happens, the brain may end up in a state of neuroinflammation, which is associated with a number of brain diseases and mental health disorders. Thank you very much. That's where we will come to a close for today. But don't forget to check out the other episodes within this series. Thank you very much. Goodbye.